Dear student, today's topic we are discussing with you the class 12th level chapter, and the chapter name is Maxima Minima. In this chapter, at first we are discussing some formula about this chapter, and after that we are discussing some example of this chapter. Now the first topic of this chapter we are discussing is local maxima and minima. That is, if the function is y is equal to fx, then a small diagram of fx, that is y is equal to fx, and some point is there. This is the p1, p2, p3, p4, p5, and their associated interval here. This is the c and the interval of c minus delta and c plus delta. Similarly here d and their associated interval d minus delta, d plus delta. Now at first we are discussing the maxima or maximum. For all x belongs to this interval, that is c minus delta comma c plus delta, and x naught is equal to c. F of c is greater than of f of x. That is, we can say if we take h is a very small number, then f of c plus h minus of f of c is always less than 0. That is, in this condition we can say f of c is called a local maximum or maxima. Similarly here, this is a local minima or minimum. Now if we discuss the interval of d, for all x belongs to this interval d minus delta comma d plus delta, that is a d minus delta comma d plus delta, then we can say f of d is always less than f of x. So from there, if we take h is a very small number, then f of d plus h minus of f of d is always greater than 0. That is, we can say f of d, that is f of d is a local minimum or minima of the given function y is equal to fx. Now we move to the next part. Now we are discussing the necessary condition for maxima minima. I repeat, the necessary condition for maxima minima. If y is equal to fx is a given function, then at the point x is equal to c, we get the maxima or minima, and if f dash c is exists, then f dash c must be 0. That is, f dash c will be 0 if we want to find the maxima minima value. This is called the necessary condition for maxima minima. Okay, we will move to the next. Now we are discussing the first example of the day. The first example is that fx is equal to xl cube plus 1 by xl cube have max and mean value, and the maximum value and the max value is lesser of mean value of given function fx. Now by the given condition fx is equal to x cube plus 1 by x cube. Now f dash x is equal to 3x square, and this will be minus 3 by x square, and double derivative is f double dash x is equal to 6x, and this will be plus 6 by x. Now for the max or mean value, for max or mean value For max or mean value, f dash x is equal to 0. So 3x square minus 3 by x square is equal to 0. That is x to the power 4 minus of 1 is equal to 0. Now x to the power 4 is equal to 1, that is x square is equal to 1. Now x is equal to plus minus 1. If we find f double dash minus 1, then we get minus 6 by and minus 6, that is a minus 12, less than 0, and that is x is equal to minus 1 point give us max value. And f double dash x 1, that is 6 plus, we are putting here the value of x, 6 plus 6, that is a 12 greater than 0. So at the point x is equal to 1, point give us mean value, that is the minimum value. Now if we find the max or mean value, then f of 1 is equal to 1 by 1, that is a 2, and f of minus 1, that is a minus 1, and 1 by minus 1, this will be minus 2. So if we put x is equal to 1, then this gives the minimum value. So this is the minimum, and when we put x is equal to minus 1, then we get maximum. So this is the maximum, so the maximum value is less than minimum value. Which is our equation. So we can say the maximum value minus 2 is always less than of 2. There is a maximum value is lesser of minimum value of the given function y is equal to fx. Now we move to the next example. Now the second and the last example of the day we are discussing. The last and second example is so that fx is equal to mod of x at the point x is equal to 0 has minimum value, but f dash 0 does not exist. So by the given condition y is equal to fx is equal to mod of x, and we know that the mod function mod of x is equal to x when x greater than 0, mod of x is equal to minus x when x less than 0, mod of x is equal to 0 when x is equal to 0. Now the right hand derivative at the point x is equal to 0 is limit x tends to 0 plus f of x minus of f0 divided by x minus x0. If we put the value of fx when x greater than 0, then we get x minus 0 divided by x minus 0, that is limit x tends to 0 plus 1, that is a 1. Similarly, left hand of f dash 0 will be limit x tends to 0 minus f of x minus f of 0. divided by x minus 0. If we put the value of fx when x less than 0, then you get minus of x minus of 0 divided by x minus 0. That is the limit x tends to 0 minus, and this is the minus 1. So this is the minus 1. Now right hand derivative and left hand derivative is not equal. So f dash 0 does not exist. So we are proved the first part, that is the f dash 0 is not exist. Now we are discussing about the minimum value of the given function of f. Now the second part of the given problem or example is when x greater than 0, then f of x is equal to x, because of mod of x is equal to x when x greater than 0. So we are using here, and now the derivative of fx is equal to 1, which is greater than of 0, and when x less than 0, then the mod function f of mod of x is equal to minus x when x less than 0. So when x less than 0, then f of x is equal to minus of x. So f dash x will be minus 1, which is less than 0. So at the point x is equal to 0, from left to right, the value of f dash x change from negative to positive. So in this condition, we can say at the point x is equal to 0, fx has a minimum value, which is our equation of minimum value. Hope the given information and the example of this chapter will help you to understand this chapter better when you practicing this chapter. And this video extend your knowledge about this chapter and help you to understand this chapter better in future. Okay.